My name is Chris Fisher, and my co-authors are Lorraine Borghetti, Joseph Hauk, Christopher Stephens, and Leslie Blaha. The title of our presentation is Comparing Classical and Quantum Probability Accounts of the Interference Effect. This research was funded by the Air Force Office of Scientific Research. We'll be discussing a phenomenon called the interference effect, which has been observed in decision-making. Interference effects violate the law of total probability, which is a law in classical probability theory, or CPT. Wang and Busmeier 2016 proposed a model based on quantum probability theory, or QPT, called the Belief Action Entanglement Model, or BAE, to account for this violation of CPT. They showed that the BAE provides a better account of interference effects compared to several competing models based on CPT. Given that there are multiple ways to formulate a model based on CPT, our primary research question is whether it is possible for a model based on CPT to provide an account of interference effects. Before proceeding, we will define interference effects. An interference effect occurs when the marginal probability of a decision depends on the presence or absence of a preceding decision, leading to a violation of the law of total probability. The law of total probability states that for event A and event B, the marginal probability of A is the sum of the two ways A and B can occur together, A and B plus A and not B. The Euler diagram below illustrates why this must hold. In the diagram on the left, the probability of A is the green area. In the diagram on the right, when event B is considered, the green area for event A is partitioned into two parts whose area must sum to the green area in the diagram on the left. We will consider two models which are based on different probability theories. One is based on CPT while the other is based on QPT. The model based on CPT is called the probability theory plus noise model, or PTN. According to the PTN, memory is organized and operates consistently with CPT, except noise in the retrieval process can produce violations of CPT. Prior research shows that the PTN can account for violations of CPT, such as the conjunction fallacy. Our primary research question is whether the PTN can also produce interference effects. The BAE is not subject to the law of total probability because it's based on QPT. In QPT, events are based on subspaces of a vector space rather than sets. In the BAE, interference effects emerge from a combination of action utility and entanglement between actions and beliefs. The categorization decision paradigm is commonly used to study how categorization interferes with subsequent decision-making. On each trial, participants see a face and must decide whether to attack or withdraw under three different sets of instructions. The faces belong to either the good category or the bad category. Participants do not know the category to which each face belongs. However, they can infer the category from facial features such as width. For simplicity, we will define type G as a face associated with the good category and type B as a face associated with the bad category. In experiment 2 of Wang and Busmeier 2016, type G faces and type B faces had a 60% chance of belonging to the good category and bad category respectively. In all cases, feedback was given. In the decision-only condition, or D for short, participants simply decide whether to attack or withdraw. In the explicit category condition, or XD for short, participants are given the true category of the face and then decide whether to attack or withdraw. In the categorize then decide condition, or CD for short, participants categorize the face as good or bad before deciding whether to attack or withdraw. The table below illustrates a pattern of interference effects, sometimes called the critical asymmetry. The critical asymmetry is an interaction between condition and phase type. In the XB condition, the interference effect is positive for type B phases and is negative but approximately equal in magnitude for type G phases. In the CD condition, the interference effect is positive for type B phases but approximately 0 for type G phases. In the PTN, events are encoded in memory and tagged with properties. For example, an experience for event A is tagged as A. To judge the probability of event A, multiple memories are retrieved, and the relative frequencies of memories read as A serves as the probability judgment. The tree on the right illustrates the process of retrieving and reading a memory. Probability of A is the true subjective probability for event A, and B, which ranges from 0 to 0.5, is the probability that a retrieved memory is read incorrectly. For example, there is a B chance that A is misread as not A. When V equals 0, the PTN follows classical probability theory. The judged probability, denoted JA, is defined below the tree, which is the sum of the branch probabilities leading to A. According to the PTN, complex events such as conjunctions have a small amount of additional noise denoted as delta. The sum of V and delta is given by epsilon, which must range between 0 and 0.5. In the D condition, participants simply decide whether to attack or withdraw. We will denote a category as Z, which could be D for bad or T for good. We will denote the phase type as TQ, which could be TD for a type D phase or TD for a type D phase. The equation on the right is the probability of attacking given phase TQ according to the PTN. This equation and others that follow are adapted from Costello and Watts 2016. In the XB condition, participants are given the true category of the phase before deciding whether to attack or withdraw. The equation on the right is the probability of attacking given phase TQ and category V. The extended error probability epsilon is used because the conditioning event TQ and V is a conjunction, which is a complex event. In the CD condition, participants first categorize the phase as good or bad. Next, they decide whether to attack or withdraw. The top equation on the right shows the probability of assigning phase TQ to category Z. The probability of attacking given phase TQ and category Z is equal to the same expression for the XB condition. This implies that the model treats the category the same regardless of whether it is given by the experimenter or judge. This important constraint will be discussed shortly. As shown on the right, the BAE model consists of 4 basis vectors defined in a Hilbert space. The orthonormal basis vectors correspond to 4 combinations of action and category. 4 utility parameters represent the subjective value of attacking a phase of a given type and category. The standard implementation assumes that for type B phases, the utility of attacking a phase in the bad category equals the negative of the utility of attacking a phase in the good category. The entanglement parameter aligns beliefs and actions, which produces an interference effect under some utility values. The probability of categorizing a type B phase as good or a type B phase as bad is defined by parameter J. In addition to interference effects, we will also investigate what we call the conditional attack equality property, or CAEP. The CAEP states that the conditional attack probabilities in the XD and CD conditions must be equal given the same face type and category. Long and Busmeier 2016 reported that this equality does not hold in their experiments. The CAEP is a core assumption of the PTN because it holds for all parameter values. By contrast, the BAE is consistent with any relationship between conditional attack probabilities in the XD and CD conditions. We will use a method called parameter space partitioning, or PSP, to explore which qualitative patterns of interference effects the models can produce. As shown on the right, PSP identifies regions of a model's parameter space associated with qualitative patterns. For example, if the mean reaction time in one condition is larger than another. PSP is useful for identifying both patterns a model can produce and patterns a model cannot produce. The number of patterns a model can produce can be used as one measure of flexibility. In the categorized with side paradigm, there are a total of 81 potential interference effect patterns. In total, there are 3 types of interference effects: positive, negative, or approximately 0. There are 81 total patterns because there are 4 types based on face type and condition. To explore how different parameters contribute to the interference effect patterns, we will create submodels by imposing constraints on the parameters. The models are indexed according to parameter constraints, where 1 indicates a constraint and 0 indicates no constraint. For the BAE, we consider one constraint, which is whether the utility of attacking a type D face in the bad category is equal to the negative of the utility of attacking a type D face in the good category. For the PTN, we consider 3 constraints, leading to a total of 8 submodels. Constraint 1 sets V to 0, constraint 2 sets delta to 0, and constraint 3 sets the true subjective probabilities equal to the objective probabilities defined by the experimenter. This is also known as probability matching. The table on the right shows the results from the parameter space partitioning analysis for all 10 submodels under consideration. The constraints for each submodel are listed in the table. We identified 3 interesting findings. First, to answer our primary research question, the PTN can produce interference effects, including the critical asymmetry. Second, unconstrained versions of the PTN and BAE can produce all 81 patterns. Third, the BAE can produce the critical asymmetry with fewer other patterns. Next, we tested the CAEP using data from experiment 2 reported by Long and Busmeier 2016. Recall that the PTN predicts that the difference in attack probabilities in the XD and CD conditions is 0 given the same face type and category. The BAE does not make a specific prediction for the CAEP. We use a hierarchical Bayesian model to test the CAEP. The figures on the right show the group posterior difference in attack probability for each combination of face type and category. The dashed line represents the PTN's prediction of 0 difference. In 3 of the 4 tests, the 95% highest density interval does not include 0, which contradicts the predictions of the PTN. To recap, our primary research question was whether a model based on classical probability theory can produce interference effects. To answer this question, we analyzed the PTN model, which assumes that memory is consistent with classical probability theory, except for noise in the retrieval process. We identified 4 key findings. First, our parameter space partitioning analysis shows that the PTN can produce interference effects by adding noise to a memory system that otherwise adheres to classical probability theory. Second, unconstrained versions of both models can produce all possible patterns of interference effects. Third, the BAE can produce the critical asymmetry with fewer patterns. Fourth, the PTN's predictions for the CAEP were not supported. Our main finding is that it is possible to produce interference effects with the PTN, which assumes that memory operates consistently with classical probability theory, except for noise in the retrieval process. Distinguishing between models based on classical and quantum probability theory can be challenging. We found that the PTN can also produce interference effects. The most significant difference between the PTN and the BAE was the CAEP. However, the CAEP is not an inherent property of models based on classical probability theory. Future work should focus on identifying strong qualitative difference between models based on quantum and classical probability theory. Thank you for your attention.